Let me also share my screen. Yes. And so I hope you have all managed to find this file there.
Yes, sir.
Okay. Yeah. And what I thought we will do is we'll go through these exercises and we'll solve some of those. So this is like a tutorial class today, as I had announced in the last class. And what I also will have is the chat window is open. So you can always ask me questions there. Okay. So I will also open. Okay, let's start with the exercises. So, in the first exercise, I asked you to define a language, okay, mathematically using that set builder notation in some properties of this. So here you can use the number of times A occurs in a word X denoted by hash A of X as a notation, and you are supposed to define a language of all words where if you count the number of occurrences of A and number of occurrences of B and you take the difference, the absolute value of this difference is at most 2. Okay, that is A can exceed B by 0, 1 or 2, or B can exceed A by 0, 1 or 2, but no more. Right? And you have to write down this language mathematically, and then you have to construct a DFA to recognize this language. Okay, so you will be able to do it. Okay, here is the DFA given to you in the table form, and you have to describe its language. So try to solve that somewhere. We have in the exercise 3, there are 4 bullets. And first one has got 3. You don't have to solve all of this. This is just for practice. You can solve some of these, but here some description of the language is given, and you are supposed to construct a DFA for it. So let us try to solve the last one. Okay, so this one. So our alphabet is of course 0, 1, and where we want all those words where letters 0, 1 and 1 occur in that order, but not necessarily consecutively. So somewhere in the word a 0 should occur, and after that somewhere in the word a 1 should occur, and after that somewhere in the word a 1 should occur. This is the language, right? Now what will be the let me open this journal. Let me change the paper style to graph. Now, what will be the automaton which will recognize this language? So, what do we want? Oh. Excuse me. Yeah. Okay. So our alphabet is 0, 1, right? And what we want sequence 0, 1, 1 to occur somewhere in the word with something in between, maybe before and after, right? This sequence of letters should occur. What would be a DFA for this look like? Any suggestion? So of course we have to start with a start state as 0, and then what can we do? We want this letters 0, 1, 1 to occur somewhere in the word in that order with some things in between, which can be further zeros or ones. So what? Any suggestion? I think today being tutorial, you can speak up. Let me see who all are here. Yeah, there are 5 of us here. So Piyush, you want to have a try? Piyush, can you unmute yourself? Hello.
Hello?
Yeah, Piyush. Okay, I think
Sir, this
Piyush
is Ishan.
I know this is Ishan. I was asking this to Piyush, is not there. Sujit is there? Sujit?
Yes, sir.
Okay, Sujit, let's give this a try. No, I mean, just this is, all. So what we want to do is we want to recognize all sequences made out of letters 0 and 1, such that somewhere a 0 occurs, and after that somewhere a 1 occurs, and after that one more position is there where 1 occurs. And we want a DFA for this.
Okay,
So I think we want somewhere a 0 occurs, we can as well latch on to the very first 0, no?
yes, we will. Yes, sir. H on to first 0.
So how do we do that?
Sir, but after S naught, it might be because before 0 there can be some numbers.
Yeah. But so what letters can be there before 0? We have only alphabet 0 and 1.
Means 1 can be there before.
And arbitrarily many ones, right? So till ones occur, we stay in S0.
Okay, yes.
Once we get a 0, we know that this 0 is already found. So this is kind of done. Right?
Right.
And we
Then
go to a state S1. Now in S1, we are looking for a 1.
yes.
So what should we skip while we are
At
in
0
S1?
it should skip, means
What should it skip when it is in S1?
0.
Okay, so I'll put a self loop on 0. So it'll skip all the zeros which occur after this first 0, and then it will wait till it gets the next one, which means this is discharge.
Yes.
Right?
And again
But,
1, S2 and 1.
S2 and 1 we skip, right?
Yes.
0.
Sorry, 0 we skip.
Sorry, 0.
Right. And then if we get one more 1, then we are done. Then we go to the final state. And after that, what can happen?
0 and 1 in closed loop.
Anything can occur, right? 0 or 1.
Yes.
And this is a DFA where from every state on every letter we have defined a transition. So this will exactly recognize those words where there is this 0 somewhere, followed by a 1 somewhere, followed by a 1 somewhere. Suppose we had alphabet 0, 1, 2, then you can modify this, right? So this kind of questions are asked. Okay. So good. I think we solved this example. Okay, what about this 3B? 3 bullet. Set of all over 0, 1 which end with a 0, 0. But we want a DFA this time. Okay, so let me try. Let me start. What is the question? All words ending with 0, 0, right? Now an NFA for this would be easy, no? What would be an NFA recognizing this? You'll have state as 0. You guess that now 0, 0 is going to come. So you go to S1. On another 0, you go to S2. And this is the final state. And nothing should come here. And before that, we can skip arbitrarily 0 or 1 non-deterministically. So somewhere where the letters are occurring, you keep skipping them till at some point you get a 0, this 0, and you guess that this is the second last 0. Okay, so this is an NFA. Recognizing all words which end with 00. Any confusion here?
No.
Okay, so Parth, now, but we actually want to want a DFA for this. So one way is, of course, we can determinize this, but can we directly try and construct a DFA which will end with 00? Okay. So we can start with S0, okay, and till we get a 1, of course, we will skip, right? Because it cannot be there. If we get a 0, possibly this is the second last 0, right? And we can go to S1. At this point, if you get a 1, then what happens?
Return to S0.
Return to S0. Exactly, 1. If you get another 0, then you go to S2.
Final state.
This is final state. But after this, if a 1 occurs,
Return to S0.
S0. If a 0 occurs after this,
return to S2.
Return to S2 itself, right? Because this remains a candidate. You know, maybe this was not the second last, this was the second last, right? And any number of such zeros till, you know, you are getting sequence 0, 0, 0, 0 after 1, you know, it's fine. You know, there is still a word is ending with 2 zeros. But if a 1 occurs, then you have to start afresh. So this is the DFA for it, right? So I think that is the correct answer, Parth. Okay, so we've done that. Let me go back to the exercise sheet. These were simple examples. Now I want to do something a little more complicated. You know, where am I? I'm in Cozen. Sorry, I should be in homework. Right. So I want to do exercise. Now, you know, in 4, I've given some examples of some problems where constructing DFA is a little more involved than before. And we are going to try and solve 4 second bullet. Okay, so binary strings X, that is strings over letters 0 and 1, such that each binary string represents a number which is denoted by X hat. Correct? So let me open this. Let me start a new page. So what we want is binary strings over binary numbers, right? That is binary. What is a binary number? It belongs to 0, 1 star, right? It's a word over alphabet 0, 1 star, right? So, and for a string X, you know, the corresponding number is denoted by X hat. Number denoted by X, right? So for example, what is 101, hat of 101? What does this denote? So I will ask one of you to try and help me out with this. So maybe is Piyush back? No. Sujit? There are very few of us, but Sujit, what is
Yes,
what 101 denotes which by number? Binary 101. Are you aware of 5, right? Right. What about 0110?
Sir, 6.
Right. So leading zeros are allowed. Huh? You can pad any number of zeros. Now you are, you know, when you process this number by finite automaton, you are processing it in this direction. So the most significant bit is read first, then the next most significant bit, etc. Right? This is the thing. Yes. And what we want is a language L of all binary strings X belonging to 0, 1 star, such that x hat is divisible by 3. So will this be so will 0110 be in the language?
Yes, sir.
So 0110 belongs to my L. What about this?
No.
101 does not belong to L. And I want to accept all the binary words which belong to language. So the language is clear. Now what we want is a kind of DFA for L. Okay. So how do we do that? And I don't expect, I mean, if you have some suggestions, I'm happy to hear, but you don't worry if you can't instantly come up with the answer. We'll slowly work into this problem. Yeah. Hi.
Maybe we can have this three states where each state denotes the remainder upon
Okay.
dividing by
Okay.
3.
Okay.
Then
Okay.
appending one symbol, we can get some sort of formula for what's the remainder when we add a symbol.
Absolutely. Absolutely. That's the answer. But that's very terse. For those who have not seen this before, let's do this systematically. So the suggestion is following, let's have 3 states. So I will draw them in blue. State S0, state S1 and state S2, right? That's the idea. And what is the property we want? We want, given a string x, if delta hat of x starting from, of course, the start state is S0. Starting from S0, if you process state x, where should you be? If you are in S0, then this implies that x hat equal to 0 mod 3. Now this notation you should get used to it. This is a bit used in number theory. It says that the remainder of x hat when divided by 3 is 0. So modulo division by 3, x hat and 0 are the same. That is, if you take x hat and divide it by 3, and if you take 0 and divide it by 3, the remainder is the same. This is what it means, right? So little bit of notation, but I think it is best you learn this because this is used a lot in maths. Okay, so the binary number represented by the word x, if it is such that the number x hat is divisible by 3, that is the remainder is 0, then you will be in state as 0. This is what it is saying. Similarly, the other property is what? Let me again write it. Delta hat of x S0 is equal to S1. That is after processing string x. If you wind up in state S1, when will this happen? I can say this equivalent to both ways. Yeah. X hat is equal to 1 mod 3. So this 1 mod 3 confuses you. It just says that x hat divided by 3, the remainder is 1. Right? So, and similarly, delta hat of x, you always start with the initial state S0. When are you in S2? When the remainder is 2. So is the idea of what we want these 3 states to do clear to you? Any confusion here? Okay. So I hope you are kind of clear about the design of the states S0, S1 and S2, right? Now, suppose I have got, we will do some little bit of exercise. Suppose I have got string 0000. What number does it denote? It denotes number 0, right? And 0 when divided by 3, the remainder is 0. So I should be in state S0 when I process sequence of zeros, right? Initially the string is epsilon. I have not seen any zeros and I'm in S0, right? If I get number 0, 1, 0, 1, then which state should I be in? After string 0, 1, 0, 1, which state should I be in? So I think Rani is here. Hi, can you answer this, please? You can unmute yourself.
Yes, sir.
So after processing string 0, 1, 0, 1, by this design, which state should we end up in?
0.
Why will it be? You mean S0, S1 or S2? One of these three states you should be in, right?
Yes, sir.
So what is the this hat? What is the remainder of this binary number when divided by 3? 0, 1, 0. This represents which number, by the way? Can you tell me that? 5, right? Sir. 5 divided by 3 will give you with remainder 2.
2.
And if the remainder is true, you should be in state as 2.
Yes, sir.
Okay, so after this you should be in 2. After this 0, 0, 0, you should be in S0. Here you should be in state S2. Huh?
Yes,
agree? So this
yes,
is
sir.
the kind of design we did. Now what we will do is we'll rely on the following property of the number. Suppose I have a string X and I know which state it winds up in, right? And suppose I get a longer string X followed by a digit 0, binary string X followed by 0. What number will this denote? You know, binary numbers have this property. Whenever you right append a 0, you double the number, right? If you've got 101, that denotes 5. If you add a 0, this will denote 10. 2 times 5, right? So actually will denote X hat. Is this a problem for you? Is this equation okay for you?
Yes, sir.
And what about X1? This will be equal to, so Sujit, what number will string X1 denote in terms of the number denoted by X?
The 2x plus 1.
Exactly. Star plus 1, right? Now what we do is, you know,
Yes.
suppose we take the remainder of the left hand side and the right hand side. What happens? That is what we want to do. So what we work out is the following. Let me see if I can go a little bit down and create some space, right? So if X hat is equal to 0 mod 3, what do I mean by this? That the remainder of X hat when divided by 3 is 0. Okay, if that is the case, this implies that what? What will this be? Mod 3. What will be the remainder of 2x? If the remainder of x divided by 3 is 0, then if I double the number x, the remainder will still remain
0. Remainder 0.
0. So this will also be 0, right?
Yes.
Is this clear? Anybody is confused about this? Suppose my number was 6110, right? And the remainder of this divided by 3 is 0. If I double this number, the remainder will still remain 0, right? So no rocket science there, just a little bit of notation, which means if I'm in now, whenever I'm in state S0, whenever the number X hat had 0 remainder. So if I was in S0 and then if I get a 0 after that, I'm going to remain in S0 because the remainder remains 0. Do you agree? I hope this transition is very clear to you. It is by this property. This property A gives you this first transition that I have drawn. And what happens if I have a number X 0 hat will be what? What remainder will I get for, number x1, binary number x followed by digit 1. What will be the remainder of that when divided by 3?
1.
1. Any confusion there? This is property B. So what transition should I get? If I'm in S0, that means the remainder of the bits I've seen so far, is 0. And then I get a number, digit 1 after that. I will go to state
S1.
S1. So this, and that is by this property B, right? Okay. Now suppose you are in S1, so you have to do the calls. If x hat is equal to 1 mod 3, that is the remainder of x hat divided by 3 is 1. Then what happens when I double the number? Remainder will become? Well, the remainder was 1, you are doubling it, right?
Yes, right.
So you will get 2. Right? Is that clear? If you had a number like 4, 100, number like 4, whose remainder when divided by 3 is 1, if you double the number 8, then you will get 2 as the remainder, right? So these are basic properties of numbers. And so if the number had remainder 1 and you get a digit 0 after that, you should go to state S2 because now the new remainder will be 2 after doubling the number. So this is by property C, and this arrow was added by property C. Okay. Okay. Somebody answer me, when I get a 1 here, what will I get? What will I get here?
0.
Yeah, actually I will get 3, 2 plus 1, but that modulo 3 will give you 0 back, right? Remainder cannot be 3. We can once again divide by 3 and get remainder as 0. So if I get a 1 here, I will go to S0, and this is by this line D. Okay, got it. Okay, so I worked out this. Now you tell me what will be the transition. If the remainder was 2, and if I get a digit 0 after that, I double that remainder 2. What will I go to?
In S1.
S1, excellent. So on a 0 from S2, I will go there. And somebody else answer what happens when I get a 1 from S2?
Self loop.
S0.
No. See, remainder was 2. When you append a 1, what happens? You double the number plus add 1. So remainder, which was 2, will become 2 times 2, which is 4, plus 1, 5. 5 means remainder is 2. So from S2, you will remain in S2, Rani. Saw the logic? Whenever we append 1, the number actually changes like this. So on a 1, you will remain like this. And if we want everything to have be multiple of 3, then which state should be the final state?
S0.
S0, right. So this is this 3-state automaton actually recognizes all binary numbers which are divisible by 3. Clear? Cozen has a whole lecture on this. This is called lecture number 4 in Cozen book. So first half of that lecture is just giving what is given in this slide. Okay. So this is a little more complicated design, but you got an idea of how to design, automata for some complicated problems. Okay. So this is one of them. Any questions about this? So if I ask you how to extend this to all binary numbers which are divisible by 5, you will be able to do it? How many states that automaton will have?
5.
5. All representing remainder 0, 1, 2, 3 and 4, right? and you can do the same trick there, and you can build the automaton. So now you know how to do it, for numbers which are divisible by anything. You can build an automaton like this, and numbers which are, binary numbers which represent numbers which are multiples of some number can all be done using finite state automata. So this is giving you some idea of what some finite state automata can do. Okay, we'll move on to the next question. Yes, please.
If the number that we're dividing by is composite, then we can do better than this structure, right? I mean, we can decompose it into factors and try to solve each individual problem.
Yeah, but you are given this binary string. How will you factorize that binary string?
No, not a binary string. Like I meant that suppose you want to find numbers
Whether it's a multiple of 3 and whether it's a multiple of 6. So first you'll find if it's a multiple of 2 and also
2 and then
So to do this, and first you will construct an automaton which detects multiple of 2. You will build another automaton which detects multiple of 3. And since you want both of these, you want to take intersections. You will take product of these two, right?
Yes, sir.
Yeah, it can be done that way. That can be done that way. You are right. Okay. So I think that's interesting. And actually, if you go through Cozen, I only suggested some of the exercises. He gives some very interesting problems to design. I will not go through this first one. This first dot is something I don't want you to actually build the automaton for that, although you can. You just have to conceptualize what that automaton will look like. It says that everywhere in the word, if you take any block of 5 consecutive letters, it should have at least 2 zeros in them. Okay, you have to build a DFA for that. So you have to think a little bit in order to do that. Okay. Yeah. Okay, let me skip ahead. Some of these exercises you can try by yourself. Let me try to do this 6. So far we are building DFAs, but now I allow you to also build NFAs and even epsilon NFAs where convenient. So for each of these 5 bullets, you have to build an epsilon NFA. But of course, every NFA is also epsilon NFA and every DFA is an NFA. So where not required, don't use epsilon or don't use non-determinism. Okay. So you use any of these 3 kinds of automata as convenient. Alphabet is always 0, 1. Okay. And let me try to solve the second bullet. That is, letter 0 can only occur at positions which are multiple of 3, but letter 1 can occur at any position. So let me clarify the question. Oh, oops, I'm sorry. That was the wrong thing I pressed. So I will start with a new page after. Okay, my alphabet is always 0, 1, and I want a word like this. So suppose I have a word which is 0, 1, 1, 0, 1, 1, right? So this is the word, right? What are the positions in the word? I will number the positions as 1, 2, 3, 4, 5, 6, right? And depending on the word, these position numbers can grow, but it will be some finite number, right? And what I'm claiming is that if you look at positions which are multiple of 3, that is this position, then a 0 can occur at those positions. So it cannot occur at position 1. It cannot occur as position 5. At position 3, the letter may be 0 or 1. So I have no restriction on when the letter 1 occurs, but I have restriction on where 0 can occur. If a 0 occurs at a position, that position must be a multiple of 3. So this word actually does not belong to the language. So my language is words where 0 can occur at positions divisible by 3, right? But 1 can occur anywhere. Anywhere, right? So can you give me a word which belongs to the language? What about this word 111111? Will it be in the language? Piyush?
Maybe yes.
Yes. Well, what if I change this to a 0?
Yes.
Yes. Okay. So the thing is clear. Now, how do we build an automaton which will do this? We want to use a DFA or NFA or what?
So I have an idea for an NFA.
Bolo.
Yeah, so we'll have 3 states, S0, S1, S2.
Right. And
Uh,
I will, if you will allow me, I'll draw it here.
Starting state will be S0.
Yes. Who is speaking,
and
by the way?
Ishan.
Ishan. Okay.
Yeah.
Now,
So on the one you will transition to S1 from S0.
yes.
Then on another one you will transition from S1 to S2.
Okay.
And on a 0 or a 1 you will transition from S2 to S0. And all states will be accepting states.
So I'll have 2 transitions, right? 1 on 0 and 1 on 1. Sometimes this is also written as 0, 1, and then you don't draw this, huh? So just to simplify the drawing. And this is, which is the final state?
All of them.
All of them are final states. Because all of those words, even epsilon is accepted till it violates this condition. And why is this an NFA and not a DFA? I see only one transition from every state.
No, so S0 on 0 has no transition.
Right. So everybody, this looks like a DFA because from every state on a letter there is at most one transition, but this is a partial DFA. From some states on some letters there is no outgoing transition, right? So this is what is called a partial DFA. And every partial DFA is an NFA. So Ishan is right in saying that technically this is an NFA. To turn this into DFA, what you have to do is you have to just add one extra state called reject R, and all missing transitions you send there. Right? And then you stay there. That's like, once you've got a wrong thing, you can never recover from this error. Once you've got a, 0 at a wrong position, then you go into this. So now you've got a proper DFA. Without that R state, what we had drawn was a partial DFA, which is technically an NFA. Is this difference clear to everybody? Rani?
Yes, sir.
Yeah. So you
Sir,
could have
yes,
built directly this DFA by adding this extra reject state. Very often we allow you to build partial DFAs, assuming that all the missing transitions go to a sync state where you remain forever then, once you enter the sync state. Okay? Yeah. So this is the automaton which will recognize that language. Any question regarding that? Okay, I think you guys are on board, so that is nice. Let's go ahead. I mean, so far we've been dealing with, I think, since there are only 5 of you, can you please type in chat if these questions are easy or very easy, okay? Just so that I get an idea of, what you feel. So these questions are easy, right? Okay, let's consider something more. 6C. Okay, letter 0 occurs at least twice, but letter 1 occurs at most once. So all words over 0, 1, over alphabet 0 and 1, where letter 0 should occur at least twice, but 1 can occur at most once. So we want to build an automaton for that. Any? So let's start. New page. This is 6C. 0 at least twice and 1 at most once. Oh boy. 1 second, I'll let the dog out. Dog. Okay. So how will we do that? We can directly try to build this automaton, but the operative word is and, which is this property should hold for the word and this property should also hold. It looks like an intersection of two languages, right? So what one approach is that we can build an automaton for the left hand side property, an automaton for the right hand side property, and we can take their product. So is the approach clear? Now somebody is going to help me build a DFA which recognizes all words over 0, 1, where 0 occurs at least twice. So who is present at the moment? Let us see who is still there. Participants. Okay, Piyush, you want to have a go? So we want an automaton which will recognize this language. 0 should occur at least twice, and the alphabet is 0, 1. So of course the start state will be as 0. Hello, Piyush, you are not there. Sujit?
Oh, yes, sir, trying.
Yeah. So we want at least 2 zeros.
We will start with the first 0 as usual, means to S1.
Okay, and if a 1 occurs, what will happen in S0?
Sir, if 1 occurs, then it should terminate. Yes, sir, self 1.
Right, so I will skip all the ones. When we find the first 0, we know at least 1 0 has come. So S1 denotes that state where we have so far seen 1 0. Right?
Yes, sir.
Now what should we do?
So at least twice.
So far we have seen 1 0.
So again, sir, if 1 comes, then self.
Okay, very good. Self loop on a 1. Very good. And if a 0 comes,
to S2.
yeah. And now we have seen 2 zeros.
Yes.
So
At least.
Then what happens?
So sir, if any of 0 or 1 comes, then it will self.
And this is a final state, right?
Yes.
So this is the DFA recognizing where 0 occurs at least twice. And that was Sujit. Now Parth, can you give me an automaton for 1 occurs at most once? So I'm going to draw that in blue. So I will start with a state called T0 there. Okay.
For 0, self loop.
Very good. And if a 1 occurs?
T1 next.
Correct. So you go to T1 if a 1 occurs. Now we have seen 1 1, right?
Self loop
On
for 0.
Okay, very good. Self loop on 0. And if another 1 occurs?
Reject.
Okay, so I go to a state called reject, right? And on reject, if a 0 or 1 occurs, then?
Return to self loop.
Okay, so I have a 0 or a 1 here, right? So this is right.
And
now, which are the accepted states? Very
T1
good. Excellent. Very good. T0 and T1 are accepting states, right? Yes, final states. So this is the automaton for at most 1 1. And then if you want all words which have both of these properties, what do we have to do? We have to take the cross product automaton, right? Which will recognize their intersection, right? So what will that automaton look like? How many states will it have?
Nine.
Rani? So what will be the start state of that automaton, product automaton? It will be a state. See, the set of states of the product automata is the set of states Q1 of the first automaton cross product with set of states of the second one. That is ordered pairs of states where the first state comes from the first automaton and the second component of the pair comes from the second automaton. And we start with an initial state of the first automaton and an initial state of the second automaton. You can do cross product of NFAs also, huh? But here we have two DFAs. So start state is going to be S0 and T0, right? Agreed? And this is going to be my start state of my product automaton. Now on a 0, where will I go from this product state S0, T0? Where will I go?
S1 T0.
S1 T0.
S1, T0, exactly. And on a 1, S0, T1.
S0.
Right? And that way now I'll develop S1 T0 further and develop this further. So I can complete this diagram, right? That is how you do the product. Okay, I will not finish the construction, but you can do it, right? It's a little bit cumbersome. You get 9 states, but still, you know, it's not too bad. You will take maybe, you know, 5-7 minutes completing this, right? So taking, you know, building DFAs for joint properties, you can, if you can directly guess the DFA for it, do it. But otherwise you break it into these components and do it. Okay. If I had an OR here, what would you have done? At least 0 occurs at least twice, or 1 occurs at least at most once. Any suggestion if in place of AND we had an OR? So I should not write there because OR of above two properties. Remember, we can take union of the languages of the two automata, that is satisfies this property or this by building an epsilon NFA by transiting either to the start state of this or start state of this. So we add one more state in that case, you know, called W0, and from that on epsilon we can go to either S0 or we can go to T0, and we reproduce both these automata as they are here, right? So that epsilon NFA will recognize the OR of these two sublanguages. That's clear? Fine. So OR kind of properties can also be done. I think we have gone that far. Let me move ahead. Right. I will not go further. Okay, next I have got 8C. Okay. So here we have to construct regular expressions for the languages which are given in English, right? And there are 5-6 examples here, but let's take the third one. Words obtained by deleting 0 or more letters from this word, right? So firstly, can we have a regular expression for whose language contains exactly this one word 10110? Let me start with a new page. One zero one one zero, right? What is the regular expression whose language will give regex alpha such that language of alpha contains only one word 10110. So anybody can come up with such a regular expression? Sujit? So I'll write regular expression in red. So I'll use the atomic expression 1 and I'll catenate it with 0. Then I'll catenate it with 1, catenate it with 1 and catenate it with 0. So this regular expression, what will be its language? Sujit? I think you have to get comfortable guessing the language of a regular expression. Huh? So how do we calculate language of this regular expression? Well, we've got this sub expression 1. What is language of the expression 1? It contains a single letter word 1, right? What is the language of 0? It contains a language which has only one word, and that word has length 1. It consists of a single letter 0. So what is the language of 1.0? It will take this language and catenate it with this language. That is equal to L of 1 catenated with L of 0. Yeah, which will be what? Just 1, 0. That is, pick up an element of L1 which contains only this one word 1. The second one contains only unique word 0, and when you catenate them you get 1, 0, right? Similarly, you keep catenating with more of them, and so this regular expression, please understand, in blue I have written the word, in red is the regular expression, and these dots are usually omitted, you know, but so we can also write this as 1, 0, 1, 1. It looks like the word, but it's a regular expression. And this regular expression gives me exactly the language containing this one word, right? So far, are you with me? I think this is the easy bit. Now, given this word, I will call this as X, this word X. From this X, we want to delete some letters, and we can delete arbitrarily many letters. Okay, so I will call this as delete of X. Delete of X will give me a set of words. Each one is obtained by deleting some letters from this. So if I delete 0 letters from this, I'll get back the original word, right? So I will definitely, original word will be in delete of X. Suppose I choose to delete the first letter 1 from X. So I will get 0, 1, 1, 0. This will also be a letter in this. Suppose I choose to delete the last letter from the word. I will get 1, 0, 1, 1. This will be in the language also. Suppose I delete, keep only the first and the last letter, deleting everything else. I will get 1, 0. So all such, letters will be in my delete of X. So is the notion of delete of X clear to you? Parth? Hello, Parth? I lost you.
Sorry. Hello. Here deleting X means we can delete 0 or more digits.
Yes,
Means
0 or more
only-
letters anywhere in the word.
Okay.
So you get different words when you delete different letters, no?
Yes.
So you take the whole collection and that gives you the language delete of X. Okay. Now when I write in English something like this, you should be able to guess that that is what I mean. So I'm saying word obtained by deleting 0 or more letters at arbitrary positions from this string 10110, right? And that is what is called delete of this X. Sorry, where is it? I am in the wrong tool. Yeah, sorry. Yeah. So given word X, delete of X is a language which is obtained by deleting 0 or more letters from this word at arbitrary positions. Correct? Now we already have regular expression for X, right? I want you to build a regular.
0 or more letters means only 0 or more
No,
than
no.
0, 1.
No. Okay, that the letter 0 is being confused with 0 or more. What I mean is you can delete, letters at arbitrary positions.
Okay.
Any number of positions, including, now none of the positions you may delete, in which case you will get back the original word, right? If you don't delete anything. If you delete the leftmost letter, you will get one word. You will delete the rightmost letter, you will get one word. If you delete both leftmost and rightmost, you will get another word, right? So those are the words obtained by deleting, letters at arbitrary positions from X. Is that clear to you?
Yes, sir.
And in fact, I can define delete of a language L, okay, which is also over 0, 1 as as what? Union of all x's belonging to L, delete of x. That is, I take any possible word in L and then I do delete over that word and I'll get a set of words. I'll keep collecting all of this for all words in the language and I get this giant language called delete of L. So delete of L is clear to you for a big language L?
Yes, sir.
Right. But currently we are talking only about delete of this one word x which is given to you. Now my question is, what is the regular expression for delete of x? So Parth, you want to have a go at this, or Rishi is here? Rishi has joined us. Rishi, are you on board with this? Have you heard what I've been describing as the problem? You can unmute yourself, Rishi. Okay, I'm not able to reach you, Rishi, so I will have to fall back on Sujit. So what are the kind of words that you can get in delete of x? In place of one may occur or may not occur, right? So how do we write an expression to recognize the pattern one may occur or may not occur?
Epsilon plus 1, and we can concatenate those
Epsilon
expressions
plus
for all
1
the
will say
letters.
optionally a 1, right? So 1 may occur or not. After that we have a 0 which may or may not occur in my delete. So I can catenate this with epsilon plus 0, right? So epsilon plus this letter means this letter is optional, right? And so I have this pattern followed by this pattern where the first pattern says 1 is optional. It may or may not occur, but it can occur. Second one says next 0 is also optional. Then we can do followed by 1, which is 1 plus epsilon is same as okay, followed by 1 plus epsilon, followed by 0 plus epsilon. So what does this regular expression denote? It says I can have up to 5 letters. So I have possibly an epsilon in the first position or a 1 to begin with. So this first letter may optionally occur. The second letter may optionally occur. The third letter may optionally occur. The fourth letter may optionally occur, and fifth letter may optionally occur. So this is the regular expression which is recognizing delete of x, right? Okay. So is the regular expression for delete of x clear to you? This is the answer. This here is the answer to the question. And now I ask a little more general question. Suppose you have a regular language. L. Huh? How do you show that delete of L is regular? Okay, so this is typically the kind of question which is asked, Now how will we do that? I showed you the trick for this one particular word, but now we are given a regular language L. So any suggestions? So these are called closure properties. So regular languages are closed under this delete operation. That is what we are saying. Now, if L is regular, then delete of L is also regular. Now, what does it mean to say that a language is regular? It has what is the definition of a regular language? It is recognized by a DFA, right? So we can assume that for L there is a DFA, there is an automaton M such that language of M is same as my L, this L, right? Don't confuse this L here. This is the language of machine automaton M is same as my language L, right? Now, given this automaton, I want to show that delete of L is regular. So I must construct an automaton which will recognize delete of L. Any idea how this can be constructed? So Parth, you want to have a go?
No.
Let's give it a try. Suppose I give you this language which says A followed by a B. You go to final state, and then anything occurs, A or B, you reject. Okay, where you stay in A or B. Okay, this is my automaton. And what language does it recognize?
A star B.
A star B, right? Arbitrary number of A's which you skip, and then you get the B, and this B should be the last letter. After that, if you get anything else, you will reject. Okay. Okay. Now what we want to do is, any of these words in A star B, we can omit those. We can delete those, and still we should be accepting. So what can I do structurally to this automaton? Wherever in the original automaton I was getting an A, I can instead do that transition on epsilon also, right? Epsilon means that letter becomes optional. And here I have got B, which is also optional because I can delete any letter, right? And here on A, B, epsilon, I can go to reject, and then on A, B, epsilon. So you add epsilon to every transition, which makes that letter optional. The result is a non-deterministic automaton, but you can show that if the original automaton had an accepting run, you would have a run on the delete of that word in the new automaton. Why? Because wherever you deleted a letter, you could have taken the epsilon edge. So any accepting run in the original automaton M, this is my M prime. M prime will recognize delete of L. Why? Because wherever, if I have a accepting run in M, I can mimic that run on delete of the word which was giving that accepting run by taking the epsilon transitions where letters have been deleted. So this is how you get it. And if there is a run here which takes you to the accepting state by some epsilons, those epsilons occur at position where there was some letter in the original automaton. So I can plug in those particular letters and I would get an original word which was from which this deleted word came. So you can argue out that M prime will exactly recognize the delete of L, and hence this is the automaton for delete of L. So given an automaton M, you can do some surgery on it to produce M prime, which will recognize delete of L, which shows that delete of L is also regular. So these are the kind of closure properties that you have to solve on. I think, any questions here?
So this method won't work if we have an NFA, right? Like we need a DFA for this.
No, even on NFA this will work. Why will this not work on NFA? If you suppose here I had this on A comma B.
Yeah, like
right?
if we already had an epsilon NFA, then
We retain those epsilons.
Yeah, but how are we sure about the epsilon which corresponds to a letter in the original word that's omitted versus just a normal epsilon transition?
So what you have to prove is if there is an accepting run in the original automaton M on some word X, right? Okay. Then on delete of every word in the delete of X, there will be an accepting run in M prime. Now, if original was an epsilon automaton and you had an accepting run on a word X, basically you had a run with some mixture of epsilons and letters of the word, right? At some positions there would be epsilons and at some positions there would be letters. And on that you had an accepting run, right? Agreed?
Yes, sir.
Since M prime is retaining all the transitions of the original automaton, clearly the language of M prime is a superset of language of M. Because we are not deleting any transition, we are only adding transitions, right?
Oh, yes, sir. So if
The
it
other
was
way is
an
more tricky to
epsilon
show.
NFA, yeah,
Yeah.
so if it was epsilon NFA, then it's not that easy to show M prime will be a subset of M, right?
Yeah, but not so difficult also, no? Suppose we assume that there is some y belonging to the language of M prime, right? So by using some epsilon transitions and some letter transitions, maybe another 2 epsilons, in M prime, you reach from the start state, T0 to the final state TF, right? Now, some of those epsilons are epsilons which correspond to original epsilons, and some of these epsilons come from the deleted letters, right?
Yes.
Because what will be an accepting run in M prime? It will consist of a sequence of moves where some of the moves correspond to either the epsilon or the letter as in the original automata, and it will have some additional epsilons where letters were there in the original automata. This is what would have happened. Agreed?
Yes, sir.
Huh? So, of course, whenever there is an accepting run, mathematically we can guess that, these epsilons came from the original automata and these epsilons came from, are the ones that you have added. Only those 2 kinds of epsilons can be there, right? And wherever there was this epsilon which corresponds to deleted letter, you can substitute it by a letter in the original automaton and you will get an accepting run in the original automaton. So my claim is that if you have an accepting run in M prime, then you can always guess, there will always exist. I'm not saying that you constructively guess, but there will exist an accepting run in M. So the languages are the same. Sorry.
Oh, okay. Yeah. Yes, sir.
That is what you are.
Yeah. So my confusion was that
can we algorithmically check?
no, not this. That my confusion was that not basically for some epsilon and letter sequence in the epsilon NFA. Not all of the corresponding DFA runs will be accepting. So there just has to exist one. So
Right. Okay. So we've done this exercise. This was good. Let me go to exercise 10 and 12. You are more used to. So you are given an NFA like this. Okay. This is an NFA with what is the size of this NFA, Rani?
Sir, can you hear me?
Yeah, I can hear you. Yeah, please.
Sir, there are 4 states.
Yes. So the size of NFA is number of states. So its size is also 4. Okay.
Yes, sir.
Yeah. Now what you are asked to do is to convert this into a DFA. So, we had the subset construction, right? And what we will do is we'll do 1 or 2 steps of this, not too many. So why don't we do that? So I will add a page. This is exercise number 10, right? And I will draw that automaton again. So I have got S, T, U and V, right? And then I've got letters A or B. And then what have I got there? I've forgotten. Let me check again. It is A. Okay. And this is the final state. And then I've got 3 transitions on letters A, right? And on A. So what is the language recognized by this, Rani? Alphabet is AB.
Sir, B A star.
Pardon?
B dot A star.
B dot A star. No. B dot A star will also have a word B only in it. So if we can, but B is rejected by this, right? Because the only run on B is you go from S to S. And that doesn't take you to the final state V. V is the only final state. Let me write the letters of these transitions in red so that you can see better. A. And this is an A and this is a B, right? And there are 4 states. So what this says is non-deterministically, you know, it will guess that this is the third last position, and from there the letter should, only way you can reach V is by 3 A's, right?
Yes, sir. It should end with 3A.
Yeah,
Language
exactly.
should-
So you are right. So if I want to write a regular expression for that, what will I write?
Sir, X, A.
Yeah, so X you give as, you know, either letter A or B repeated arbitrary many times. You can't write X in regular expression. So the way to
Yes.
give arbitrary string is either A or B, letter A or letter B repeated arbitrary times, followed by a
A.
A, right? And
Yes,
this
sir.
is the regular expression for the language of this. So it's also important that you are able to convert, you know, automata into regular expressions. We have done, you know, algorithms to do this, but intuitively also you should be able to convert. Huh? So this is clear. This is the language. Now we have to do the subset construction
Sir.
on this. Yeah. Hi.
Can we write also A star, B star, A?
A star, B star.
Yes.
See, this will not recognize the following word. For example, if I've got BAB, huh? A. This is a word which will be accepted by the automaton.
Yes.
Because I skipped this. But here, you know, you are saying there is a sequence of 0 or more A's followed by 0 or more B's. So I am not allowing BA pattern to occur there.
Okay.
So what you can do is actually you can put arbitrary number of A's followed by a number of B's and star of that. Okay.
Yes, sir. Right. Yeah.
And in fact, there is an identity in regular expression which says that B plus A whole star is equivalent to A star, B star, whole star. This identity is true. So you could have substituted this sub expression by this sub expression. So you are right. You can do it that way, but you need that extra star. Huh? Okay.
Right.
Yeah. Please ask. Somebody
Yes,
is.
sir. It's clear, sir.
Okay, fine. Okay. So now we want to construct, you know, a deterministic automaton for this. What is the deterministic automaton? What are its set of states? Rani?
Sir, it's got 2 power 4 states.
Yes,
DFA
right.
has-
So basically subsets of this set STUV, right? So I have
Yes,
this
sir.
set STUV and all possible subsets, but we are, you know, we will keep only the reachable states. So we will not write all these
Yes,
states.
sir.
So what is the set of start states of this NFA?
Yes.
S. So my start set in DFA is just the set containing a singleton S, right? This is my
Yes.
start state of my DFA, right? Now, both on letter A and B, I must tell where I will go, right? So this set of states S on A will go where, Rani?
S, comma T.
Yeah. So I will go to the set S comma T, huh? Right? From S on an A, I can go to S. On a B, where will I go?
Yes.
S. Very good. Right. So S I have already got and I have expanded it, but this ST is a new set. So now I need to add ST to my list because it's a reachable state in DFA. Now I need to expand this. So one more step. So I don't know if Piyush can, Sujit, you want to tell me where ST goes on A? For checking where ST goes on A, I have to check where S goes on A. And then I have to check where T goes on A and I have to take union of these two, right? So where does S go on A? We already checked that.
ST and T on A is U.
Yes, so I have
STU.
to add that also.
Yes.
So I get this STU as the set. And where does ST go on a B?
ST S and only S.
Very good. So these are correct transitions. Now I got one more STU, right? So now STU on an A will go to what?
Sir, STU and V.
Yes, very good. And on a B?
Only S.
S, very good. And STUV on an A will go to?
Sir, same STUV.
And S.
Yes, yes.
Right? And okay, so I've now got a table which is closed. Although I had, as Rani said, there would be 16 subsets, only 4 are reachable, right? Now, which of these are the final states in DFA?
STUV.
Right, because that's the only one which has non-empty intersection with the set of final states, right? So you are right. This is the final state, and I should write an F next to it. Okay, showing this is the, so this is how you convert this into a DFA. So I think that is clear to you. When we have an epsilon NFA, the procedure is a little more involved, and let's take an example of that. I think then we can finish. So I think for some of you this is easy, but okay, here is an epsilon NFA. Let's take this. See, I can give you the NFA by means of a table like this or by means of a diagram like this. You shouldn't have any problem. This table just says that from the state P on epsilon I can go to QR, on an A I go to empty set of states, on a B I go to Q, and similarly from Q on epsilon I go to empty set of states, on C I go to states P and Q, right? So I can draw either the diagram or I can give this transition table. And you should be able to apply the procedure on either. That's easy. Here I have an epsilon NFA, right? And what we want to do is we want to convert this to a DFA using the extended subset construction for epsilon transitions. So can we do one step of this, not too much? So I will add a page. Exercise 12. And what was the automaton? Now I don't remember that very well. Q0, Q1, Q3, Q2. Okay, weird numbering. Q0, Q1, Q3, Q2. And I had a move here on, I had a move here, and then there was a self loop, and there was a move here, and there was a move here. And I think this was on an epsilon, this was on an epsilon, this was on A and epsilon. This is initial state, and this was on a B, and this was on a B. And then this Q3 was the final state, I believe.
Yes,
Yeah?
sir. Yes.
And there was no outgoing transition.
Yes.
Yes, okay. So this is my automaton. Now we want to convert this to a DFA, right? So I will have a table. Sorry, let me change color. I will have a table where, my sets will be epsilon closed states. Now, what is my initial state of my DFA? Here the initial state is just Q0. Right? The initial state of an epsilon DFA corresponding to an epsilon NFA is what? You take the set of start states of this epsilon NFA, which in our case is just Q0, right? So, but there could have been more than one start state. So you take Q0, and what do? You do something called C epsilon of this. That is the epsilon closure of this set of start states. What will be the epsilon closure of this set of Q0?
All the
Q0, Q1, Q2, Q3.
Right. So I'll get all the states. So I'm going to here write down the epsilon closure of the set of start states Q0, Q1, Q2, Q3 as my start state. I can start in this set of states. Why is that? Because initially I can take epsilons and I can reach any of this. So I can begin absorbing the letters of the word after doing these epsilons by transiting to any of these states, radioactively, right? So I can start in either Q0 or Q1 or Q2 or Q3, right? Because of these epsilons, which is why this is my start state in my DFA. and then I've got two letters A and B. So what happens on an A from this set?
Q2.
From an A, Q0 will go to this thing and nothing else has got an A transition. So I will just go to Q2. On a B,
Q2, Q3.
Q2, Q3. And actually it is not enough to write this directly. I should take the epsilon closure of this. But it so happens that from Q2 there are no epsilon transitions, and from Q3 also there are no epsilon transitions. So this remains same. But actually I have to take the closure of these sets that I reach, because I can take further epsilon transitions after making the lettered transition. So is that clear to you? That is the method. So now I've got two other sets here, a Q2 alone and a Q2, Q3. So I have to do work out transitions from that, but you will be able to work it out yourself. I will not complete this table. But remember here, after calculating this, from a set on a letter where all you go, you better take an epsilon closure of that set. That is the method. Okay. And then which final states will be those in which there is at least one Q3, right? So the first one will be final, this Q2, Q3 will be final, but not the Q2. Okay, so I think you can work out this example yourself in full detail. This is the idea. What else I wanted to do? Yeah, I wanted to do, we are coming to an end of this tutorial. I wanted to do 15.1. The prefix. No, I wanted to do 15.2. The second bullet. Okay, so let me explain this. The exercise is fully described in Cozen, something called miscellaneous exercise number 28 at the end of the book. You can read it there, but let me explain to you, what Cozen wants us to do. Page after, and this is exercise 15B. Right, the second bullet of the exercise 15. What he says is, you want to do. I am going to. I am going to call this language as del1 of a language L. So suppose L is a language. Alphabet is 0, 1. So you have got binary, binary alphabet, and you have got words over this. What is del1 of, and you are given some language L over it. Okay, then what is del1 of L? Del1 of L is all words XY such that X1Y belong to L. Is the definition of del L clear? So let me give you an example. So this is an example. Let L equal to the language 0, 1, 0, 1. Yeah, this is or 0, 1, 0, 1. Right. This is my language L. Then can anybody tell me what will be del 1 of L? Sujit? So what happens? You have to pick up a string which is of the form x1y. That is some, there is some 1 in the string, and the things to the left of it are called x, and the thing to the right of it are called y. If you find such a word in my L, then I delete that 1 and I retain that x followed by y. Now there can be several occurrences of 1, so there are several ways in which I can delete that 1. So, what will be the language I'll get here? Well, 0 is not of the form which can be broken into x1y, right? So 0 will not contribute anything to del 1. I have got a word 0, 1, 0, 1, right? So I can actually pass that 0, 1, 0, 1 as following thing. I will call this as x. I will call this as y, and there is a 1 in between, right? And then I will retain x followed by y here. So I will add here a 0, 0, 1 in my language by deleting this 1. The other thing I could have done was the following. For the same word 0, 1, 0, 1, I could have taken this one. In that case, this string would be my x. Sorry, this would be my x. There is an epsilon after this, which I take as my y, and this one I delete, right? So if I delete that, I will take x followed by y, which is 0, 1, 0 followed by an epsilon, which is 0, 1, 0, right? So my del 1 of L is this. Agreed? So it's the idea of, words, from L which have at least 1, 1 and obtained by deleting one of those ones. That is called del 1 of L. Is the definition of del 1 of a language clear to you? Who is not clear? Did you see how we got these two words? We got both
Yes,
of them from this word, and 0 did not contribute anything. I think if you don't ask, I will assume that you know this one, right? So I think the definition of del 1 L is clear to you. Now, what I want to prove is if a closure under del 1 L is regular, then del 1 L is regular. I want to show that if my original language was a regular language, the language obtained by deleting 1, 1 in each of these words is also regular. So is the problem clear to you guys? Do you have another class now or something? Anybody?
No, sir.
Can
No,
we
sir.
continue for 5 more minutes?
Yes, sir.
Yes, sir.
This is the last exercise I'm going to do.
Yes, sir.
Okay, so the claim is these are some of the little more intricate problems I'm asking. You have to show that regular languages are closed under this operation del 1. Okay. I could have defined a different operation called del 1 prime, where I delete all occurrences of 1. I could have done that also, no? So that is a different definition, but here this is my definition of del 1 of L. And I want to show that if original L is regular, the new one is regular. Now, how do we normally do it? Any suggestion? So we are given that L is regular, which means it has an automaton. Agreed? So let M be DFA for L. We construct epsilon NFA M prime for del 1 of L, right? So we do surgery on this automaton M to obtain another automaton M prime, which will recognize del 1 of L. This is what we have to do. Now, how do we do that? Remember, we are allowed to delete exactly 1, 1. So the idea is the following, and very often you have to only express the idea. Take the original automaton as it was, it has a set of states Q, right? And some transitions inside, right? Maybe this is on 0, this is on 0, this is on 1. I will call this state as, S1. Let me write those states in red so that you can see S1, S2, S3, S4. Some such transitions will occur, right? Do you agree? My automaton, I'm assuming there is a graph, automaton graph, which is like this. There will be some start state and this will be there. What I do is, yes.
Here we can made it by putting epsilon with pair with 1. Am I right?
Yeah, but suppose this occurs in a loop, then that epsilon can be taken several times. So you will delete several ones, no? So your idea that this one can, we can add an extra epsilon in place of 1 is good. But the trouble is, if that one transition occurs in a loop, then that epsilon will be taken several times. So you will delete several ones. So we want to make sure we delete exactly one. So you're in the right direction, but one more trick is needed.
Sir,
Who is speaking? Yes, Ishan.
maybe we can sort of make 2 copies of the automaton.
Excellent.
That's
Yes. So we make
exactly
second
one
copy
epsilon
of the
term.
automaton. It also goes exactly like this, right? But every time you want to delete that one, no, you have a copy of here S1. Let me write it in red. So now you have a prime copy of all the states. So here you will have a state called S1 prime. You will have a state called S2 prime. You will have a state called S3 prime. And you will have a state called S4 prime, right? And it will have same transitions as the original automaton, right? So this will be another copy of the automaton. Now we have got a copy, with original set of states and a primed set of states. Okay. You will have all of this. But what happens is, because you want to delete this one, instead of going to this S4, you go to the deleted copy. So you go to this S4 on an epsilon. So what happened was, to remember that you have gone to this S4 by deleting 1, you will take this epsilon transition. You are going to a prime copy of this S4. So prime copies say that so far we have deleted 1, right? And then you exactly do the same transitions as in the original automaton, not deleting any further. So you just have an epsilon transition from every outgoing edge with a 1. You instead have an epsilon transition going to the Q prime part, which will go to the prime copy of the target state. Is the construction clear? Piyush? Here from S2 I went to S4. Additionally, in the new automaton, I will go from S2 to S4 prime on an epsilon. And then from S4 prime, I will do exactly the same transitions as in Q. So I will have in Q prime the same transitions as in Q. And additionally, I will have this epsilon transition going from the Q part to the Q prime part on a 1 letter. And I can do this epsilon transitions only once, when I move from the left half of the automaton to the right half of my automaton M prime. So my M prime will have set of states Q union Q prime. Q will be a copy of the original automaton M. Q prime will be a copy of the original automaton M. And additionally, wherever I had delta of any state S, on a 1, this is in my original automaton M. If it took me to a state T in my new automaton, I will also add this additional transition, delta of M prime S on an epsilon, I will go to T prime. Okay, so I will add this extra transition. And of course, I'll keep the copies of the old transition. And the final states will only be final states within Q prime. Right? So I have to delete at least 1 to move from Q to Q prime. I cannot delete any further ones here. And the rest of the run remains as before. So I'll do part of the run before deleting that one in the Q part of the automaton. Then I will take an epsilon transition where I had taken a 1 transition, and the remaining part of the run I will do in the Q prime part. So this is how I will recognize del 1 of L. So is del 1 of L clear to you? This is what we did. So I think constructions like this you may be asked to do as more advanced questions in the exam. Okay. So I think this is all I wanted to do today. I hope you got a little flavor of solving the homework questions. There are many more in the book, but I think representative ones are given here. Okay. There's a very nice one called Hamming distance in Hemingway, in Cozen. This is the third bullet among the closure properties. The exercise 15.3, it's a little more advanced. It builds upon this idea of delete 1. Okay. So maybe you can read that or try to solve it yourself. Okay. Now I
Sir,
think it is yes. You ask questions now.
syllabus of the exam is up to regular language, right?
Up to regular languages, that is converting regular expressions to epsilon NFA. And the reverse construction, very simple. Okay.
Means Canny algebra also in the syllabus.
No clean algebra. No clean algebra in the test because we haven't done it at length. No clean algebra. Okay.
Okay.
Yeah. So that is the test, and the test I have slightly reduced the marks because we are going little slow. We will have a class quiz sometimes with the remaining part of the finite automata. So instead of 25 marks, the exam will be 20 marks. Okay.
Only MCQ and numerical
Both
questions.
MCQ and working out questions, both will be there.
Okay. Means subjective also.
Yes, like we did today, the homework things that we did today.
Okay, sir.
Rani?
So will you be uploading solutions to the homework, like apart from whatever we can discuss?
So the recording of today's class will be available. Other questions I am not going to upload, but our exam is on Thursday, right? Thursday morning. I think 8:30 to 11:30 is the slot they've given us next Thursday. Okay. So I think there are no classes during this week. You have other exams, right?
Yes, right.
Yeah. So what I suggest is that if you have difficulty with any of the other homework, please ask difficulties either by directly sending me an email or by actually better posting it on the Q&A section. Or if you want your solution to be checked, please post it to any of the TAs or me. Okay, we will help you with your doubts till Wednesday. Okay. I think I've done a representative set of exercises and I've given it solution in today's class where the recording as well as this what I've written down will be made available just now in half an hour. So I think that should be sufficient. Yeah, Parth, you had a question?
Yes, sir. I should say okay, sir.
Yeah.
Is exam on safe, sir?
Exam is on safe. I have to learn to set it up on safe. You have given exams on safe where you have to give written answers, right? And scan the answers and upload it, right?
Yes, sir.
Yes, sir.
That is the procedure we will be using. For the MCQ part, maybe you can directly answer on the safe. Huh? And the remaining part, you can submit your written answers and we will evaluate it. Okay. Yeah. All right. I'll send out an email to all the participants with what I said about the exam, so that everybody knows, because only 5 people are here, probably because today is a holiday. Okay. Any other questions or any doubts about the things that we have done so far? Okay, if there is no more, then what I will do is I will stop recording. I think